as is introduced nicely here. Jay Lofstead from Sandia. I'm got kind of pulled into the middle of this effort. I'm with many people, I'm sure, in this room. I know a few in particular that think that trying to do something like a top 500 list for storage is a meaningful or potentially harmful activity. But I got brought into the middle of this because I saw some of the other benefits that we could hopefully derive from it. And using this kind of mechanism, I hope, gives us a way to do it. So this is kind of an explanation and an encouragement to try to get more participation, because I think there is real benefit to this in spite of how frankly useless this meaningless number is. Oops. Nope, too far. There we go. Okay. So the thing that we always deal with is that we have people in Congress, for example, in this country, that are doing budgets and telling us how much money we're allowed to spend on different things, such as our new machines. And because of that, they need some way to understand how one machine compares to another, even though they might be very different designs. And in terms of our funding for these kinds of things, having something that's internationally accepted, so that we can say, for example, the Chinese now in the top 2 spots, and then we're now in number 4 at the best spot, that gives Congress something to say, well, we're not number 1 anymore, we need to do something, even if there's not a direct way to be able to compare those machines. So we wanted to do something similar to try to understand how different storage systems compare. So we end up having to deal with this fact that people at an administrative level may not understand all these nuances that the particular implementations of these storage systems have. So give them something that we think is a clearly imperfect, in fact, probably even problematic way to rank, in quotes, these different systems. The reality is, if you look at some of the more detailed numbers, I think those may be more useful. So the problem that we ended up dealing with, and I know others have tried to do this kind of thing in the past, and the problems they've run into is what is an appropriate benchmark, because the workloads we have on these machines vary a lot. And the thing that we came from, since the 4 of us organizers all come from a modeling and simulation environment, is let's focus on that, because that's the background that we have, and we don't know enough in terms of what would be broadly acceptable benchmarks for the data analytics side, and try to bring that in the future. So that was the kind of thing we wanted to try to figure out. So let's pick some basic workloads and work from there. Sarp gave us a lot of information about the efforts that he had tried to do previously, and made it clear to us that this was an effort that was bound to fail. And in reality, we almost did, but we managed to have some strong personalities that were intent on making sure this happened. So that was really the main reason why it happened. As far as my role in this group is, I'm kind of like the Pancho Villa, where we have the other people that are insistent on doing things that we know are completely ludicrous, but my job is to try to keep them going and going forward, because I see there's some potential value there. So in terms of what we wanted to look at in terms of benchmarking so that we could have some sort of ranking, what we looked at was, how do we buy our machines and how do we specify what we need, and use that as a way to say, is the storage system adequate for what our platform needs? And when we look at it, we say, okay, we need 90% forward progress. So that means we're allowed to have, say, 6 minutes per hour of activities that are not actually going forward with our computation from where we were last time. So we said 5 minutes is a more natural number for us when we look at a clock, so let's just use 5 minutes and base all of our different benchmarks about what can you do in 5 minutes of time. And we knew it had to be both bandwidth as well as metadata. And on the metadata side, we know there's some small file workloads where you have millions, or even these days potentially billions of small files. But you also have very large bandwidth issues where you need to write out a petabyte and you need to write it fast. So how do we balance between those two so we have something that's meaningful, well, somewhat meaningful, and provide something so that people can look at them and say that in a balanced way, this system may be better than this other system, and then give them more nuanced data so they can say, given my workloads, this system, in spite of that top number, may be better for me. So the other things that we've had many questions about as we've been trying to do this is things like the analytics workloads. And if anybody has suggestions, we'd really like to hear them. So far, nobody's had any. The other thing is people have particular biases against or for particular benchmarks. IOR seems to be fairly well accepted because you can configure it and make it work well enough to represent your different kinds of bandwidth-related workloads. MD test, there's been some particular argument within our group that said that MD test does not adequately measure interactive user experience. So it's fine if you're looking at a batch job and how it's running, but if you have a user sitting at the command line trying to do something, that MD test cannot adequately capture that experience. So there should be something else in addition. So that was another thing that nearly killed this effort, was trying to get that set up. And then there's other tasks that system administrators really care about a lot more than the end user, things like how do we do a big find to find out what we should purge, or just know what's in the system. And I don't understand that side as well. I just know that's an important activity we always specify. So how do we incorporate these kinds of things into the benchmark as well? So we have an initial test at trying to do a find, but it was something that we couldn't really get in a stable enough form to really trust it. So it's something that we put as a help us figure out and understand this so that we can add this kind of information to something we collect. So the other piece that comes up often is people are going to cheat. And we know that, and it's just a fact of life, is anytime there's been a benchmark or a competitive ranking of anything, there has always been cheaters. So personally, I think that having cheaters is a way to reveal flaws in your system, or what we tried to turn it into was a way to have people tell us what's the best possible way to use your storage system. And that, to me, I think is more interesting. So if we give people a pathologically bad example and say, show us this, and we know it's going to be bad because it's going to be bad for probably everybody, but also show us how good you can make this. But you have to tell us how you configure everything so that others can potentially try to do the same thing for their own actual production use. Then we have a way to let people say, oh yeah, that number's not good, but look how good I can do if you let me configure it the way I want. And that's also a way we're trying to help people feel more encouraged about participating, is we're not just saying, show us how bad it can be, but show us when you tune it, how to tune it, and how good it can be, so that you can see what you're truly capable of on your platform. So cheating is something, in that sense, we really want to encourage so that we get the best possible information about really not just what the storage system architectures are, but what's the best way to use them. And that's something that's not communicated very effectively, I don't think, in the community today. It's more a matter of we tune I/O libraries and our storage stacks based off of particular examples, but we don't do a good job of saying, for this storage stack, if you tune it this way, this is exactly the right characteristics to be able to make everything work great. We have anecdotal evidence about different things working well, but having something that is specifically published for exactly that kind of scenario is not really done very well. Another issue that we have is lists are frankly kind of boring, but they are important. We don't want to be the BuzzFeed of I/O, but that's kind of the direction that these kind of things kind of end up looking when you start looking at from the who's doing what cheating in quotes, of course, versus doing things on the hard list. And you'll see from the results I'll show in a little bit here that what we have is not a necessarily representative output, but it's something that gives us information to know what we need to work on as a community. And that's one of the outputs I would like to see from this effort. The driving force that originated all of this, as far as our effort goes, was Julian Kunkel, who is now at the University of Reading in England. He wanted to gather a documentation of all the different storage systems in production use today, but it was just a voluntary collaboration thing, and he was having a hard time getting people to participate. And when John Bent said, I want to do this competitive list, he asked me about it, and I said, John, I think we need to talk to Julian, because between the two of you, I think we can finally have motivation to get both ends going right. And we ended up then having this motivator saying, okay, we have this competitive number that site administrators can then point to and say, oh, my storage system is #1 in the world, or it's #2, but my compute's #1, that kind of thing. So that they have a motivation to say, it's okay to use that compute time and be on the storage system for a while. And that was one of the things we wanted to be able to enable for people, because otherwise, again, you're not going to get the time on the machines to be able to do these kind of benchmarks. And we also acknowledge that getting dedicated time is not something that's necessarily going to happen, so we need to take that into account, at least on the notes, so that people know these metrics were gathered during normal production runs. So what we ended up falling down to, just because we didn't have better options, was just the old favorites of IOR and MD test. We tried to include the additional metadata operations, but turns out that that benchmark development really didn't get done in time, and there was discussions about how to try to make it tuned correctly to represent the right things, and all of those discussions haven't really finished yet. So we just stayed with the basic IOR and MD test. And again, given the pathologically worst case, and then say, show us how to do the best possible thing with your storage array. And then combine the two of those in a somewhat defensible way so that we can give some sort of composite number that people can then look at and try to make some sense out of. So the details of it is really we have hard and easy. So the hard is the pathologically bad test, and the easy is configure any way you want, but you have to accomplish these goals. And you have a write and a read phase, and all of these pieces end up getting taken together. The IOPS score represents all of the metadata operations, including the find, and then the bandwidth score represents the IOR operation. So it's really just pure how many bytes can you push within that 5-minute time. So all of the creation and writing is bounded at the 5-minute mark, and then the read is take as long as you need to be able to accomplish the task. And then that's the measurements that we use. So if you can read a lot faster than you can write, then great. If you can write a lot faster than you can read, then that's fine too. It's just that we're looking at the right time being that 5-minute mark. For the reporting requirements, since we have this cheating phase that we encourage, you have to document all of the configurations parameters that you specified to be able to get those easy results to happen. We also want the output results from all the scripts for the hard side as well, so that we can then take that and build our composite number. The other pieces that we want is as much detail as you can provide on how your storage system exists. So for example, is it a burst buffer? Is it disk array? Is it something else? And what kind of devices do you have? What's the theoretical performance limits and things like that, so that we have this historical record that Julian was trying to put together. And I think that also can be useful for future platform acquisitions if we can look at theoretically this configuration yields this number, in a hard case it yields that number, and in the easy case with this kind of configuration we can get these results. And then people can look at that and say, okay, our workloads more closely resemble one case or the other, and get some idea of what they should be able to get in production compared to what the theoretical numbers might be based on what they want to buy. And since it's a competitive list, there has to be some sort of overall ranking. So much like the normal top 500 list, we're just going to be sheep following in their wake and say we'll have a presentation of the list twice a year, once at SC at a BOF and then once at ISC in a BOF. And should this actually grow more, we'll try to invade into the actual top 500 presentation, but honestly I don't have any expectations that that will really occur for at least several years from now. So the first list that came out, we ended up having 9 submissions, and I managed to get the one Sandia machine on there here at the bottom, and you can see it was a very small run, and that was me mainly trying to debug the benchmarks. So in spite of how poorly ranked it is, it was just more a can I get this to run kind of thing. The top one you can see is an IME system, but if you look at the, in particular, let me use this, see if that's going to work here. The bandwidth, since it's all flash, is clearly really fast, but if you look at the IOPS, it's relatively slow, and if you compare it down here to the spectrum scale machine, it's very slow. And just because of the way that the formula balances out, that really big bandwidth number ends up winning. In talking to the IBM people that did the spectrum scale test, they just had a spare test cluster sitting in the office, and they decided, why the heck not just go ahead and run the benchmarks there and see what we get? And that's the kind of numbers that they got out. So that's not a production machine, but it's more of a test machine. And it gives an idea of something that's properly configured, what you may be able to get out of it. So in terms of wanting to keep this relevant over time, we want to avoid, if possible, something that is both a mistake and a benefit in the regular top 500 compute list, and that is that the number doesn't, the formula and what the number incorporates doesn't change over time. So instead, what we want to do is say, as the systems change, let's figure out, and as the workloads change in particular, let's change what we want to do and evolve the list over time, being able to say that if we have this different balance of workloads, then let's go ahead and, that are becoming the predominant workload, let's go ahead and incorporate those as part of this benchmark so that we can then look at the systems. The quickest that we would incorporate something new would probably be on the order of 2 years. We would want to first have something that we thought was reasonable, then we'd want to roll it out over the next 6 months as a test, and the 6 months after that to have the community look at it, and then another 6 months later, after we've had some more discussion about it, look at it and say, is this something that we should include or not? So it wouldn't be something quick, even if we came up with something, because we do want some stability so that the list has some sort of meaning over time. Okay, so where this all came from, I kind of hinted at this a little bit earlier, but so back at the end of 2015, Julian came to me and said, I want to collect all this information, can you help me do that? And I said, great, this sounds like a good thing for us to be able to understand what storage platforms are out there. And we went through and pushed and tried to encourage different people to submit, and we got a handful of submissions. None of them were particularly complete or correct, with the exception of Julian's. Because of that, there was no real, I have to provide all of this information for the list. It's a, what information do I have time to dig up right now that I can put on the list? So it was hit or miss what kind of things were there. Then in June of 2016, John said, we need to create this competitive list. So I ended up connecting everything together and have been kind of a peacekeeper between the two sides. John is very driven on this competitive, we need the best side of things, and Julian is very much, we shouldn't be competitive, we should all be one big happy family and just all share, and it will be wonderful. So it's been quite a task trying to get all of that to work together. And then George Marcomanolios, who kind of came on late, he's been a tremendous help in trying to take the scripts that we have for the benchmarks and trying them out on the machines at Koust and kind of debugging them and figuring out how to make them so that they are easy to use and are fairly representative. So that's how George ends up coming into the picture as well. So this VI 4IO, so it's a virtual institute 4IO that Julian put together. Again, it's just documenting the storage system design. The best practices part was something that was desired but never really happened. And the community part, since it was just essentially a website, never really happened either because there weren't any meetings, or I didn't make any efforts to go to the different storage events and say, let's try to do this kind of thing so that we have this broader organization. So it kind of languished. Kind of mentioned this already. Yeah, so I'll skip that for now. So the overall mission of things really is we wanted to be able to provide a way to generate an excuse for people to run benchmarks in a production style workload for their storage systems and share those results with other people, provide a mechanism so that they can justify that time for their management to approve their use, and then also gather as much information about what these storage systems look like and how to use them most effectively. That's really what the overall goal is. And I think in spite of everything and how bad our core number is, I think we've kind of accomplished that goal. And so that's really the kind of thing. So I wanted to go into a little more detail on some of the different components of the benchmark because I think there's some interesting results in there. So the least degradation for IOR, easy to hard. So this is looking at the the easy test, which is configure however you want, versus the hard, which is the pathologically bad. So we can look at it and say that the IME, because it's all flash, there was really difficult to have a big difference between the two because there wasn't any mechanical things to deal with. But oddly enough, my tiny little spectrum scale example did really well. And I don't understand that one, but that's it's something that I think it may be scale related, that I was almost more dealing with cache issues potentially than anything else. But you can see we have the variety of different systems there, and there's potentially a huge difference between these bad cases and the good cases. So having some idea of what the specifics are between them in terms of configuration and how to use them is really an important thing for us to be able to document. So creating in a shared directory has been historically a difficult problem, and we wanted to be able to, since one file per process is, much to my amazement, still a very popular output technique, look at different systems and understand how well do these different storage systems compare in this respect. And Lustre ends up taking all the top spots there, which I was happy to see. But if you looked at the IME machine, it's dramatically worse in that respect. So that shows that they're much weaker on the metadata side. They're great on the storage bandwidth, but when it gets down to the metadata side, there's issues. If we look at the IOPS that they get on a per client basis, then again, IME looks really bad in spite of it getting the top number. So again, they're really a bandwidth monster. They're not really a balanced system. And that kind of gets reflected in the individual scores as well. The per client one, again, similar kinds of numbers, but that looks a little bit better on IME, but it's kind of all over the place for all the different storage services there. The per client score, this one I don't understand as well. I think it's more the combined score for each individual client on a node in terms of bandwidth and metadata operations. So that's showing that the BGFS one looks overall the best on that front. But again, it's very well mixed up based on all the different systems and configurations there. And the highest IOPS is definitely not the IME machine again. And it's that one machine, the test machine that IBM had that they are running. And again, that was one where they just said, I have this test machine sitting here, why don't I just try it out? So how that will actually relate to any sort of production use, we don't know yet. Highest bandwidth, that again, clearly was the IME one, just that was, I think, largely a hardware setup. Again, though, they also had a large number of nodes feeding it, so that's another factor that should be taken into account. In terms of the find, this one went to a Lustre system that Julian benchmarked at DKRZ, the German Climate Center, and he got really good results on that. And part of that was due to making a custom version of a find command rather than just using the standard Unix find. And that was one of the other things that we wanted to drive as part of this, is if you're going to have a special tool that's going to work well, part of the easy test is you need to share that. So that was one of the things that we have coming out of this as well. So that's what I got. If you have any questions, I'll be happy to answer them. Oh, one last thing is we have Weka IO that's supposed to be coming in with this as well. So I'm curious what they're going to do. And if any of you would be happy to participate, then we'd love to have you as well. So having some volatility in the list, particularly early on, I think is a really good thing. All right, that's all.
Okay, do you have any questions? Great.
So I have two comments. One is on your slide number 5, where you said it's relatively easy to model what applications do, and then gave an example of MD test. I'm not aware of any actual applications that does what MD test does, which is basically every run creates like a gazillion of files and then removes them. Typically, this is a poor man's simulation of like, I have a lot more ranks, each of which opens a single file and then eventually closes and maybe removes it. So that is actually not a good test. I mean, I know people act.
Better one.
Yeah, Oak Ridge has a better one. They actually have like the full scale where they open a single file per rank, and then they close it, and then they do other things with it. And I mean, there's a lot more jitter, but it's a lot more similar to what actual applications do. So you should talk to them. And I mean, I believe it's a vastly better one. And then the other comment on your tables, we can see there's like a huge difference of number of nodes. You should just include a local file system too with a node of 1, and it'll blow lots of things out of the water.
And that's one of the things that we know, because this is a voluntary effort and trying to get people to contribute. It's what kind of resources can you steal is really what it comes down to. And if you can only get one node and you can do great on it, great, but you're not going to get the total bandwidth numbers. You may get some good IOPS numbers, but you're not going to get the total bandwidth because you just don't have the aggregate bandwidth coming out of the node.
Right, but I mean, still, I think the point is somewhat valid. So either you group like systems into a similar scale to get a better idea how different things scale, or if you include everything, do include a local file system or two, so that people have an idea of what they are foregoing by going a global file system.
That's one of the things with the list that we're trying to be careful about, is that if you're going to run against a burst buffer, that's one result. If you're going to run against a centralized parallel file system, that's a different result. So unless those are an inseparable part of your storage stack, then those are different results you should report. So that's exactly one of the things we wanted to be careful about, is that having a way to differentiate between I'm running against all flash versus I'm running against disk, or God forbid I'm running solely against tape for some reason. Mm-hmm.
Comment about the flash and IME. Sorry, right?
There you are.
There you go.
Okay.
Sorry, I'm short, but I'm seated. So, so the data warp system up there is flash as well. The reason IME does so well is actually because it's got a log structured thing. That's their big trick. John Bent and I talked through this list a while ago. But yeah, that's flash is helpful, but log structured on flash is really helpful for
Absolutely.
this one. Yeah.
So, on comment on what Oleg said. Recently, we changed how we measure metadata as Oak Ridge. We are not just opening a gazillion files and just stating them and then closing them. We now are interjecting a 32K IO written into each open file and then close it, and then name that as a transaction. So create open, write, close, and then measure that one. It is brutal, and I don't think the vendors like it that much, but we don't care. That's much more realistic. So, and one last thing, we will definitely, or most likely, submit something from Spider 3 to this list. So.
It's worthwhile mentioning that the MD test that's being run also has a small data component. It's like 4K or something like that. And so it's not just a pure, open, create, close workload. And, all of the workloads that are being run are doing like read to your neighbor and things like that, so that they're not, creating and then accessing the data from the same node. The various phases are run so that you do the writes at the beginning, then you do a whole bunch of metadata creates, and then, you do the accesses and then the find at the end, so that, you have a chance to push things out of cache. So, and I mean, to Oleg's comment that, if you had a local node, and you can just run, and blow it away with one client, because you're running it for 5 minutes, if you're just, hoping to put it all into RAM, you can probably fill up your RAM in less than 5 minutes. And so, you're going to have some kind of storage IO, right? And that's why we picked a time rather than a size for
5 minutes originally, because that was something we had not really settled on. And yes, the other details about how this runs those are all exactly right. And if you look at the benchmark scripts, it does detail out how we're trying to keep this all to be as fair as possible. Yes.
As a measure or benchmark, if you will, for the, quote, pesky data analytics, I wondered if anyone has considered using a visualization tool in the sense, say VTK has been applied to parallel streaming data. ParaView reads, I think, 200 file formats. The idea would be, you know, if you tessellate a 3D thing, how fast can that be done?
That's a good idea. We've been trying to find people that do these kinds of workloads a lot to get input from them, and we haven't really gotten anything. And in our digging through the literature and such, there's not been anything stable, but that's one of the best suggestions we've heard. Okay.
Okay, well, any more questions?
And please submit. We're trying to be friendly here, so, and as you can see, the numbers can be a little wacky, and you can still do pretty well. All right.
The only other thing I would say is that, you know, we don't want to get something like spec FP or anything like that where it's super hard to set up and configure and it takes, you know, weeks and tuning and, you know, $1 million machine or whatever. The goal is, you know, benchmarks that can be run easily, and we don't want them to take hours and hours and hours to run, right? So the fun is that you'll actually get numbers as opposed to, you know, you have to take your whole system down for a week to generate a benchmark.
Yeah, basically you go to the site, then you can clone the GitHub repo, and there's a script there, and you can run it and get a result out within an hour, just based on everything running. Getting it tuned so you get the best possible numbers is going to take some time, but that's our goal, is to make it that easy to get started, and then over time you can tweak the numbers and figure out what's going on. So.
Great, well, let's thank our speaker.